of serendipity in recommender systems. First, I'm going to talk about definitions, then about experiments, then I will come back to definitions and talk about experiments again. Then I will talk about algorithms, and I will conclude by highlighting a possible future direction of this topic. Recommender systems are software tools that suggest items such as movies or articles to users. Let's say there is a user. His name is Johnny. Johnny likes the Lord of the Rings movie. But if we keep recommending to him only Lord of the Rings movies, probably these recommendations are going to be relevant and accurate. But Johnny will probably find our system boring. That is why recommender systems are optimized not only for accuracy, but also for novelty, diversity, and serendipity. We conducted literature review and found that serendipity has multiple definitions in recommender systems, but most authors describe serendipity with these three components: relevance, novelty, and unexpectedness. Where relevance indicates that the user likes an item, novelty has two variations. One is that the user is unfamiliar with the item, and another one, maybe the user is familiar with the item, but just doesn't think about this item when we make this recommendation. Unexpectedness has four variations. I'm not going to go through all of them, but just going to give example of one of them. For example, let's say that I only watch comedies, and then I'm suddenly recommended a horror movie. Then I might find this movie unexpected, because it is very different from movies that I usually watch. And not all the authors require all three components to be present in serendipity. Some authors require an item to only be, for example, relevant and unexpected to be considered serendipitous, while some other authors only require an item to be unexpected to be considered serendipitous. And out of curiosity, I decided to calculate the number of ways how we can define serendipity in recommender systems, given these building blocks and their variations. And this number turned out to be 28. And of course, not all these definitions have been used in the literature, and also some of these definitions are used more often than others. However, this gives an idea of how many degrees of freedom a researcher has when they pick a definition of serendipity. Here is an example how we can label an item serendipitous. Let's say that Johnny logs into our movie recommender system to find another Lord of the Rings movie, but instead comes across the Particle Fever movie, which is a documentary about the Large Hadron Collider. Let's say that Johnny has never heard about this movie and doesn't usually watch this kind of movies, but decides to watch this one and likes it. Then we label it serendipitous for Johnny because it meets all requirements for an item, all three requirements for an item to be serendipitous. And why would we recommend serendipitous items? According to our literature review, most authors indicate that serendipity broadens user preferences. And to give an example, to measure preference broadening, we use this statement. Watching this movie broadened my preferences. Now I am interested in a wider selection of movies. And they also indicate that serendipity increases user satisfaction. For example, I am glad I watched this movie. However, before 2018, there have been no experiments that would support these claims. That is why we decided to conduct one. These were our research questions. What are the effects of variations of serendipity and its components on preference broadening and user satisfaction? And what are the effective features for detecting serendipitous items? We didn't look at 28 definitions of serendipity, but we picked the most common definition of serendipity, which is that the item needs to be relevant, novel, and unexpected. And we looked at each variation of each component. Since there are 4 variations of unexpectedness, 2 variations of novelty, and 1 variation of relevance, this resulted in 8 variations of serendipity. We conducted our experiment in MovieLens, which is a movie recommender system where users rate movies on the scale from half star to 5 stars after they watched the movies. We invited users of the system to our survey And for each user, we picked 5 movies that were recently watched, because we wanted to make sure that users still remember their experience with these movies. Rated with at least 3.5 stars. We picked only relevant movies, and also those that are unpopular, because serendipitous items tend to be unpopular. This is the survey page that the user needed to fill in. The user needed to reply to statements regarding novelty, unexpectedness, and, for example, preference broadening. Around 500 users joined our survey and gave their feedback on around 2,000 movies. Out of these around 2,000 movies, 63 to 181 were serendipitous. And depending on the definition of serendipity, this number varied from 63 to 181. We analyzed our data and found that all variations of serendipity components, of relevance, of novelty and unexpectedness, have positive association with preference broadening. We also found one variation of unexpectedness which has a negative association with user satisfaction, and that was the variation of unexpectedness when the user doesn't think that they would enjoy the movie before watching this movie. We also found that almost all variations of serendipity are positively associated with preference broadening. And we analyzed this strength of associations and found that the strength is different depending on different variations of serendipity, implying that it is important to distinguish between different types of serendipity because they might affect users differently. We also detected effective serendipity predictors. They were the rating that Movie Lens predicts that the user is going to give to the movie, popularity of the movie, and similarity of the movie to the movies that the user watched in the past. But we haven't found that serendipity is associated with user satisfaction. But there was another study where the authors did find this link, and this is the study by Chen et al. They conducted a survey in mobile Taobao with more than 3,000 users. The authors used the structural equation modeling to analyze their results and found that relevance, novelty, unexpectedness, and timeliness, which indicates that the recommendation is provided on time to the user, these concepts are positively associated with serendipity. The authors had a separate statement about serendipity in the survey. And the authors also found that serendipity is positively associated with purchase intention and also with user satisfaction. The authors also found that user curiosity has an effect on the association between novelty and serendipity. There was also another study where the authors found that serendipity is domain dependent. The authors analyzed the dataset that we collected in our Movie Lens experiment and the dataset collected in the Taobao experiment. And they found that some observations are the same in both domains. For example, serendipitous items tend to be unpopular both in the movie domain and the e-commerce domain. But there are also different observations in different domains. For example, the more similar the movie is to movies that I've watched in the past, the less likely it is that I will find this movie serendipitous. But the opposite is true for the e-commerce domain. The more similar the product is to the products that I bought in the past, the more likely it is that I will find it serendipitous. And now I would like to come back to the beginning of the talk when I discussed definitions. The way serendipity has been defined in the recommender systems does not correspond to the original definition of serendipity. Originally, the term serendipity was coined in 1754 by Horace Walpole when he referred to the old Persian fairy tale, the three princes of Serendip. He wrote that the princes were always making discoveries by accidents and sagacity of things which they were not in quest of. Later, the sociologist Robert K. Merton collected mentions of the term serendipity from magazines and journals to investigate its use context. And in 2018, Ohid Yakub used archives of Robert K. Merton and proposed the topology of serendipity, which included 4 definitions of serendipity. To give example of 2 of them, let's say I put on a jacket and I find 50 euros in my pocket. If I had been looking everywhere in my apartment for this 50 euros, and the last place where I could think I have this 50 euros is in my pocket, this is one kind of serendipity. If I hadn't even been thinking about 50 euros and I find them in my pocket, this is another kind of serendipity. And if I had known that I have 50 euros in my pocket, this is not serendipity. And we applied these 4 definitions of serendipity to recommender systems and proposed generalized serendipity. An item is generalized serendipitous if it helps the user to achieve at least one goal different from those they set out to achieve with the recommender system. Let's say that Johnny logs into our movie recommender system to find another Lord of the Rings movie. But again, comes across the Particle Fever movie, watches it, and likes it. We label this movie generalized serendipitous for Johnny because it helped him to achieve a goal that is different from goals that he planned to achieve with this recommender system. Or in other words, Particle Fever is the movie that Johnny didn't plan to find but found and liked it. Now I'm going to refer to the definition used in recommender systems as Rex's serendipity. Rex's serendipity covers some cases that are also covered by generalized serendipity. For example, Johnny coming across and liking the movie Particle Fever. But there are also cases that are covered by generalized serendipity but are not covered by Rex's serendipity. For example, let's say that Johnny wants to explore new kinds of movies, but comes across the Lord of the Rings movie. He watched it and he likes it. In this case, this movie is no longer going to be Rex's serendipitous because this movie is not different from what Johnny usually likes. But this movie is going to be generalized serendipitous because it helped Johnny to achieve a goal which is different from the goal that he wanted to achieve with this recommender system. The key difference between these definitions is that generalized serendipity is based on user goals or based on what users want to find, while Rex's serendipity is based on these components: relevance, novelty, and unexpectedness. It doesn't take into account user goals. And we conducted a field experiment to investigate these definitions. We also included user serendipity. This definition depends on a particular user. Different users might define this term differently. And we decided that it is important to take this definition into account because it is important to understand what users mean when they request serendipity in the system. We included these 3 definitions in our experiment: generalized serendipity, which is based on user goals; user serendipity, which depends on a particular user; and Rex's serendipity, which depends on serendipity components. And here again, we didn't look at 28 variations of serendipity. We picked the most common variation of each component of relevance, novelty, and unexpectedness. And we looked at all combinations of these components. For example, we looked at unexpectedness alone, we looked at the combination of relevance and novelty, and we also looked at the combination of all 3 components. It is important to note that relevance alone is not serendipity because it is already reserved for accuracy. These were our research questions. To what extent do various definitions of Rex's serendipity capture items considered serendipitous under generalized and user serendipity? And what aspects of user behavior are associated with different serendipity types? We run our field experiment in Soli, which is an article recommender system designed for Android and iOS. And when the user logs into the application, they need to indicate their interests. And then when the user uses the application, every day we ask the user why they're using this application. The user can select their goals from the predefined list of goals, or they can add their custom goal. Then the user goes to the hub page where they can see 15 recommendations, article recommendations. 12 of these articles are within user interest, and 3 articles outside user interest. And the articles from these categories are picked randomly from the database. After reading an article, the user is asked to reply to the survey, where they need to indicate whether this article was relevant, novel, and unexpected to them, and also whether it was serendipitous, based on how the user understands this term. We also ask the user to indicate goals that this article helped them to achieve. And if this article helped the user to achieve at least one goal different from the goals that this user set to achieve with this recommender system, then we label this article generalized serendipitous for this user. The user can also interact with these articles. They can hit the like button or bookmark an article. We ran our field experiment for 16 weeks, and more than 600 participants joined our study. Around 400 of them completed at least one goal and article surveys, and we focus on this subset of our dataset. We also recorded the time spent in the system and reading progress of articles and interactions with these articles. These are distributions of goals that users plan to achieve with Soli and achieve with articles. And we noticed this peculiar observation that improve myself was the most desired, one of the most desired, but the least achieved goals. The first key finding of our study was that recommendations that should be considered serendipitous have been overlooked due to the narrow definition of serendipity used in recommender systems. And we can already see that from raw numbers. We received user feedback on around 2,000 articles, and around 1,000 of them were generalized serendipitous, around 700 of them were Brexit serendipitous, and around 800 of them were user serendipitous. To analyze this data, we used classification metrics, precision, recall, and accuracy. And we found that in the best case scenario, serendipity types only capture 2/3 of generalized serendipity. Our second key finding was that user understanding of serendipity differs from generalized and Rexis serendipity. Again, with precision, recall, and accuracy, we found that serendipity types capture, in the best case scenario, they capture just over half of user serendipity. And our third key finding was that different types of serendipity are associated with different patterns of user behavior. To investigate associations between serendipity types and user behavior, we used mixed effect logistic regression models. And we found that most serendipity types are associated with interactions and reading progress. Generalized serendipity was only associated with reading progress. The combination of relevance and novelty was associated with all measured behaviors, and for unexpectedness alone, we haven't found an association with any measured behaviors. The key takeaways of our study were that Brex's definition misses items serendipitous under other serendipity definitions, implying that algorithms optimized for one type of serendipity are unlikely to satisfy another. And another takeaway was that user understanding of serendipity differs from generalized and Rexis serendipity, implying that optimizing for serendipity might not meet user expectations of the system. Now I would like to talk about algorithms. And there are different ways how we can improve serendipity of a recommendation algorithm. One way is to change the input data of the algorithm. Another way is to change the model of the algorithm. For example, we might change the objective function of a matrix factorization algorithm. And finally, we can re-rank the results of an accuracy-oriented algorithm. But today I would like to talk about one strategy that we used to increase serendipity of a recommendation algorithm, and that was transfer learning, which we applied to neural collaborative filtering. Neural collaborative filtering consists of three parts: generalized matrix factorization, which is very similar to matrix factorization, multi-layer perceptron, and the neural matrix factorization layer. Usually, we first train generalized matrix factorization and retrieve user and item latent representations. Then we train multi-layer perceptron and retrieve the output of the last hidden layer. And then we concatenate these vectors, concatenate latent representations of items and users, and with the output of the final, of the last hidden layer. And this vector becomes an input, the input for neural matrix factorization layer, and then we train this layer. We applied this algorithm to our serendipity dataset that we collected in the movie lens experiment. In this dataset, some relevant scores are associated with serendipity scores. So we know that the user liked a movie, for example, and we also know if the user, for some movies, we know that the user found it serendipitous or didn't find it serendipitous. And we split our dataset into three parts: training, validation, and test. Since serendipity scores are very rare because it is very difficult to collect them, we need to ask users many questions to label a movie serendipitous or not. That is why there were very few of them, and our training dataset was missing serendipity scores. But our goal was to predict the serendipity scores in our test part of the dataset. So we applied common strategy. We trained this whole structure on serendipity scores of the validation dataset, and we evaluated this whole structure on the serendipity scores of the test part of the dataset. And then we improved serendipity by applying transfer learning. We trained generalized matrix factorization and multi-layer perceptron on relevant scores of our training dataset. And then we tuned this whole structure by training a neural matrix factorization layer on serendipity scores of our validation dataset. And then we evaluated it on serendipity scores of the test part of the dataset. And in this way, we improve serendipity of this algorithm. Now, if you would like to evaluate your own serendipity-oriented algorithm, here is the list of data sets that contain serendipity labels. There is a data set collected in movie lens experiment, the data set collected in the Taobao experiment, and also Serendlens, the data set that contains serendipity labels for movies and books. To label an item serendipitous, the authors used previews that users wrote when they consumed those items. For example, if the user wrote, "By chance, I downloaded this book into my Kindle," and then the authors label this book serendipitous to this user. And to annotate this dataset, they hired Amazon Mechanical Turk workers. And finally, I would like to highlight one possible future direction of the topic. Most efforts on improving serendipity of recommender systems have been focused on improving recommendation algorithms. But recommendation algorithms are only part of recommender systems. And there are also other parts of recommender systems that affect user experience, for example, user interfaces. This has also been highlighted by the recent paper on serendipity in recommender systems by Smets et al. The authors wrote that the dominant focus on algorithmic improvements in recommender systems has overlooked the importance of user interface design choices. And I believe that user interfaces can improve serendipity of a recommender system by highlighting items that are potentially serendipitous to users. And one of the ways to do that is to generate explanations. For example, let's say that we know that the user has watched the movie Groundhog Day and we would like to recommend them the movie Primer. We might generate the following explanation. This movie has more sci-fi but less comedy than Groundhog Day. Both movies have a lot of time travel. To generate this kind of explanation, we might want to use the tag genome dataset. This dataset has been introduced in 2012, and also we worked on this dataset for more than a year at the University of Helsinki and published a number of papers on this topic. The key feature of this dataset is that it contains relevance scores that indicate the degree with which a tag, such as time travel, applies to a movie, such as Groundhog Day. For example, we can tell that the tag time travel applies to the movie Groundhog Day with a score of 0.7 and to Titanic with a score of 4.2 on the scale from 0 to 1. And that allows us to compare movies between each other and generate explanations. What we can also do is that we can combine two tag genome datasets from different domains. And this will allow us to compare items from different domains. For example, we can tell that the book Hamlet has more drama than the movie Groundhog Day. And this allows us to generate cross-domain explanations. For example, if we know that the user has read the Harry Potter book and we would like to recommend to them the movie Jumanji, we can generate the following explanation. The movie Jumanji has more lions and jungle, but less England and mystery than the book Harry Potter and the Chamber of Secrets. Both have a lot of fantasy, action, and adventure. And by the way, this is an actual example I generated with these two data sets. And we already partially have investigated these cross-domain explanations. Not exactly these ones, but very similar ones in our recent CGIAR paper, which we will present this summer. In that paper, we evaluated similar explanations and found that they affect user perceptions of recommendations. That is why I hypothesized that these explanations can also affect serendipity of a system. With this, I would like to end, and thank you for your attention.